Hello class, welcome to this video on the 5.4 review. So let's go ahead and get started with the problem sets here. So problem set number one, so this lesson is about conditional probability. So let's look at first one. Two researchers asked 150 subjects to recall the details of a car accident they watched on video. 50 subjects were selected at random and asked about how fast were the cars going when they smashed into each other. For another 50 randomly selected subjects, the words smashed into were replaced with hit. The remaining 50 subjects, the control group, were not asked to estimate speed. A week later, all subjects were asked if they saw any broken glass at the accident. And there wasn't any broken glass in the accident, but they asked them. So suppose we select one of the subjects from this experiment at random. So S is smashed into wording and Y is the yes response. Okay. This is event S, and then broken glass, yes or no. Okay. So find the probability that given that they said yes, right? Given that they said yes to that there was broken glass, what is the probability that the experimenters used the word smashed into, right? Use that phrase. Let's go ahead and calculate that. So we said probability of S given Y. So remember, to calculate that probability, the formula for that is probability of S and Y divided by the probability of the given. So the probability of both divided by the probability of the given. Okay, so how many people said yes, there was broken glass, and we're part of the group where they used the word smashed into? So yes, there's so this is the yes group, this is the smashed into group, so this is the intersect, right? So 16 out of 150. Okay, so 16 out of 150 were in that group. And how many people said yes, there was broken glass? 29 out of 150. The 150s cancel, so we're left with 16 out of 29, which is 0.552. All right, so describe it. So there is 0.552 probability that given that it was the subject, given that the subject said there was glass, the subject heard the words smashed into. Okay, so that's just in my own words, but that's the main idea there. You can also say that the probability that the subject heard the word smashed into out of those that said that were glass was 0.552 or something like that. All right, so given that the subject did not receive the smashed into wording, okay, so the probability, so given that they did not, so S prime. Find the probability that the person said no. So that's Y prime, okay? So Y prime, if they did not say yes, then that means that they said no, right? Okay, so write your answer as a probability statement using correct notation for the events. Okay, so this is what we did. All right, so the probability of Y prime and S prime divided by the probability of S prime. All right, so how many people said no and did not receive the smashed into wording? So no and not smashed into. So that's 43 plus 44 out of 150. And then the probability of S prime did not receive. So the probability of those that did not receive the smashed into, in general, were these guys, right? So basically totaling these two. Oh, no, not those two, sorry. These two. These four, sorry. So those are the ones that did not receive the smashed into wording. So 7 plus 6 plus 43 plus 44. Out of 150. All right, notice that the 150s cancel out, so we just get that. And then so we'll see what that is. So we get 43 plus 44. Again, we're going to do this all at the same time. Divided by 7 plus 6 plus 43 plus 44. So we get 0.87, my probability. All right. Okay, so that's number one. So number two, do adult and juvenile eastern gray squirrels in New York Central Park exhibit different behavior toward humans? That's one of the questions, many questions investigated by volunteer squirrel sighters in October of 2018. So you got some data, whether they approach the humans or are indifferent, or they run away. And then whether they're juvenile or adult squirrels. So, okay, so we got J is juvenile, R is they run away. Find the probability that given that they're juvenile squirrels, that they run away. All right, so the probability of R given J. Again, it's the probability of R and J divided by the probability of J. So how many squirrels are run away and are juveniles? So that's 81, right? So 81 out of 2,898 squirrels. And then the probability of juvenile squirrels. How many juvenile squirrels are there? 330 out of 2898. These cancel out. So we get 81 out of 330. Let me just convert that as a decimal. So 0.246. All right, and then describe the probability in words. Given that a squirrel, or given a juvenile squirrel, the probability of selecting or of finding of running away, rather, is 0.246. All right, so given that the squirrel did not run away, find the probability that it was an adult. Okay, so probability of adult given that it did not run away. So R prime. Adult means non-juvenile, so I'm going to put, in this case, there's only two options, juvenile or adult. So J prime. So, okay, so the probability of J prime and R prime divided by the probability of R prime. Okay, so non-juvenile and did not run away. So non-juvenile, so we're looking for adults that did not run away. So here, 756 and 1241. Out of the 2,898, which you know it'll cancel, but I'm just showing my work here. And then probability of not run away. So the ones that did not run away in general, so that's these two combined, did not run away. So 867, 1379. Out of 2,898. All right, and of course the 2,898s cancel and we get our final answer. Let's see. Okay, so 0.889. All right. How's the okay? So number 3, how's the hatching of water python eggs? Okay, so we looked at this one before. We looked at this data. It's just so similar, the same type of data. Okay, so let's do the total. So 27, 56, 104. All right, and then 29. So 29 is 58, and then 160, so 187, and then this one was 129. Okay. Given that the chosen egg was assigned to hot water, so given hot water, so we'll say H is for hot water. What's the probability that it hatched? Well, no, I guess we can't really do that for hot water. Yeah, okay, so let's say T is for hot water, and H is for hatched. Okay, so given that it was assigned to hot water, what's the probability that it hatched? So again, using the formula, I'm trying to make sure you remember the formula, okay? All right, so hatched and hot. So hatched and hot, that's 75. So 75 out of 187. And then the probability of hot temperature, 104 out of 187. These cancel, so we get 75 over 104. So 0.721. All right, if the chosen egg hatched, what's the probability that it was not assigned to hot water? So the probability that if it was hatched, so if H, given H, what's the probability that it was not assigned to hot water? So T prime. All right, so probability of T prime and H divided by probability of H. Okay, so how many eggs were assigned to hatched, but were not hot? So that's these ones right here. So 16 plus 38 out of 187. And then how many were hot? So it's 104 out of 187. So these cancel. We get our answer there. So 16 plus 38 divided by 104. 0.519. Okay, all right, there you go. So that takes care of number 3. So let's look at problem set number 2. Researchers recorded data on pet ownership for a randomly selected household in a large city. Suppose that 40% of households own a cat, 32% of households, this should say dog, not cat. 32% of households own a dog. In addition, suppose that 46% of households own neither a cat nor a dog. Complete the Venn diagram for this situation. All right, so they said that 46% own neither, so that's right here. So we don't have a cat or a dog, right? So I'm going to put that right here. Okay, so 0.46. And then, okay, so 0.46 for neither. And then, and then it says 40% own a cat, 32% own a dog. So how do we get the middle? Well, so it says neither, right? So we know that they had to add up to, these 4 things had to add up to 100%. Okay, so what we can do is, okay, so we could say, well, let's add the dogs and the cats, the percentage of dog and cats, so 40%, right? 32%, and let's add this 46% in here and see what percentage is that. So this is 8, this is 118%. Okay, well, these have to add up to 1, right? 100%. So that means that this has to be 18% right here. So the reason why this is going extra is because of this. So this has to be 18%. And if that is 18%, then we can figure out the rest. All right, so that's 18%, and then we could say, okay, so that's 18, and then the dog is 40, so then it's 40 minus 18, so that's 22%, so 0.22. And then cats were 32, so 32 minus 18, that's 14%, so that's 0.14. Okay, and there's my Venn diagram. So if a household that owns a cat is selected at random, what is the probability that the household owns a dog? So the probability that if a household that owns a cat, so that's given that they own a cat, what's the probability that they own a dog? Okay, all right, so probability of dog and cat divided by the probability of cat. Okay, so all right, so the probability of dog and cat, that's 0.18 from the Venn diagram. What's the probability of cat? The probability of cat is, they said right here, cat is 40%. Oops, I think I might have reversed this. They should say 22% here, sorry. And then, because cat was 40% and dogs was 32%. So this I just need to reverse those numbers. So 0.14, 32% for dog, and then 40% for cat. So then in this case, cat is 40%, so 0.40. All right, so 0.18 divided by 0.40. So we got 0.45. All right, so number 2, this is the, okay, so random sample, 500 US adults was selected. By the way, this right here should say 129. Right here, not 429. So that's a typo. So we got 500 US adults was selected. Each member of the sample were identified as a high school graduate or as a homeowner or not. G means high school graduate, H is homeowner. Suppose 89 people are high school graduates, 119 are homeowners, 129 are either high school graduates or homeowners. Complete the Venn diagram to summarize the data based on these two events. All right, so we got so the probability of G or H, right, is equal to, using the general addition rule, the probability of G plus the probability of H minus the probability of G and H, right? So in other words, we know we had how many graduates? There were 89 out of 500. And high school, there was 119, or H is for homeowners, 119 homeowners out of 500. Then we're going to subtract the probability of both, but we don't know what both of them are, okay? We don't know how many are both. But we do know that the probability that is G or H, right, either high school or homeowners, is 129. So we do know that much over 500. So what you can see here is that we have 89 plus 119 minus X is 129. Basically, if we just look at the numerators and we say that this is X. So then how many guys do both, basically? So let's add these up. So that's going to be 208. Let me make sure that's right. Okay, so 129 equals 208 minus X. So X equals 208 minus 129. So that's a total of 79. Okay, so 79 do both. So let me see, 79 are both. And then so for graduates, there's 89 graduates. So 89 minus 79 is 10. So that's got to be 10 here. High school, there's 129, or I keep saying high school. 129 or 119 are homeowners. So 119 minus 79 is 40. All right. And then there's 500 people in total. So if I add these three numbers up, 10 plus 40 plus 79 is 129. Subtract that from 500. And that's 371, or neither. Okay. All right, so that's my Venn diagram. Now, part B, if a homeowner is selected at random, what is the probability that the person is a high school graduate? All right, so the probability, and now homeowner. So probability given that they're a homeowner, what's the probability that they're high school graduate? Okay, so probability of graduate and homeowner divided by probability of homeowner. Now there's 79 that are both, right, out of 500. And homeowners, how many homeowners are there? 119 homeowners, right? So it's out of 119 divided by 500. So cross that out. So 79 out of 119. So you get 0.664. All right, for your answer. All right, so number 3, a recent census at a major university revealed 60% of these students may use Macs. Okay, so this is what we had before. Now we don't have to necessarily use the Venn diagram, but we, it makes it easier. We can just use, this rule, right? This formula. So find the probability. Suppose we randomly select a student from the census who uses a Mac. So given, so M is for Mac, and G is for graduate student. Okay, so the probability. So given that someone uses a Mac, what's the probability that they're a graduate student? So let's use that formula. Graduate and Mac divided by the probability of Mac. So how many Mac users are there? Well, 60%. What's the probability of that they graduate and they mainly use a Mac? They're a graduate and mainly use a Mac. So it says 23% of respondents were graduate students who said that they use Macs. So that's 0.23. All right, and then so we got 0.23 divided by 0.60. So 0.383. All right, no Venn diagram necessary for that. We just used a formula. All right, so we're at the last, we should be at the last, there should be one more problem set. And this problem set refers to independence. How to tell if two events are independent. 35 students in Mr. Tabor's statistics class completed a brief survey. One of the questions asked whether each student was right-handed or left-handed. So we got female and right-handed. Are they independent? All right, so we'll say F is for female and R for right-handed, okay? So probability. We're going to determine, okay, given that they're right-handed, what's the probability that they're female? And then we're going to do probability, given that they're female, what's the probability that they're left-handed? Okay, so that's one way. That's one way to test whether they're independent or not. Okay, so all right. So looking at the females, given that they're right-handed. So how many right-handed? So let's do that. Let's do the totals. This is 5, 30, 35, 14, and 21. Okay, so a total of 30 right-handed. Given those right-handed folks, how many were female? 18. So we got 18 out of 30. Now let's do the left-handed. So given the left-handed, there's 5 left-handed. So given them, how many were female? 3. All right, so we got 3/5 here. Divide this by 6. And notice that we get the same fraction. 18 divided by 6 is 3. And 30 divided by 6 is 5. So if these two are equal, that means that they're independent. Okay, so that means the two events are independent. The two events, female and right-handed, are independent. Okay. All right, so let's look at the second one. Baseball star David Ortiz, nicknamed Big Papi, was known for his ability to deliver hits in high-pressure situations. Here's a two-way table of his hits, walks, and outs. All right, are the events hit and post-season independent? So we'll say H is for hit, and then T is for postseason. Okay. So all right. So what's the probability that, given that they're in postseason, that he gets given that he's in the postseason, that he gets a hit? And then we're gonna do the probability. Well, we need to get the totals. So let me do that over here. What's the probability that he gets a hit, given that it's not the postseason, meaning it's the regular season? We're going to compare those two. All right, so let's add these up. So if I add these up, I get how many total hits? So 0. So we get 2,100 hits there, or 2,110 hits. And then it says, okay, it doesn't actually tell you how many. So let's do the how many non-hits. Let's add up these numbers. I'm just going to do that here. 1531. Okay, so given hits, right? There's 2,110 hits. Given those hits, how many were postseason? 87. So out of the 210, 87 were postseason. Now let's do the non hits. The non-hits. So that the non-hits are the walk and the outs, right? So that's these. Given these, right? So out of those, basically I have to add those two together. So let me add those two together. I'll just do it here. So out of those guys, those two, the walks and outs, how many of those were not in the regular season, or not in the postseason rather? And the answer is these two, right? 1474 plus 5034. Okay, so let's see what those numbers are. So 3008 over 6773. So we get 0.444. And let's compare that to the first fraction, 87 out of 2110. Look at that, 0.041. So big difference. If we're looking at hits, right? Given that it was a hit, what's the probability that it was in the post? Or I'm sorry, given that it so given that it was a hit, what's the probability that it's in the postseason? It's a 4% chance that it's in the postseason, given that it was a hit. But then when you're looking at the regular season, look at that. He has a greater chance of getting a hit, right? So there is a relationship between those two. So that means that these are not independent. In other words, they're dependent. All right, so let's do the last one. So the Titanic struck an iceberg and sank on its first voyage across the Atlantic in 1912. So we got survivor, the classes, and then whether or not they survived. Are these events independent? Meaning, is there a relationship between what class they were in and whether or not they survived? We're going to calculate this using probabilities, okay? All right, so we're going to say that S is for survived, and F is for first class. All right, so what's the probability that they survived given that they were in first class? We're going to compare that with what's the probability that they survived given, well, we're just going to say what's the probability that they survived. This time we're going to do it differently. You can say the probability that they survived given not first class. I'm just going to do the probability that they survived. So I'm going to switch it up. Okay, this is another way to do it. All right, so how many first class survivors, or how many first class people? We're going to add these up. So that's 319. So that given 319 first class. How many survived? 197. Okay, we'll figure out what that is as a decimal later. Let's do the survival. How many survived? We need to add these up. Well, yeah, so yes for survival. So we'll add those up. Again, you can show your work, but I'm doing it over here. So it's 442 out of, again, show your work, actually write it out, what you're adding. And then let's add up all the numbers. So 122 plus 167. So these are the non-survivors. So add the non-survivors with the survivors. We get 1207. Okay, so this is out of 1,207. All right, and then let's compare those fractions. 197 out of 319. So we got 62%, almost 62% chance that they survived if they were in first class. Now, if I look at just survivors in general, I get 36% survival rate in general, right? So there's 36% that survived. Notice that there's a difference in those numbers, and that means that it's not independent. In other words, it's dependent. It does depend on what class you're in, whether or not you survived, right? Notice that when they were in first class, they had a high chance of survival. Whereas if we just looked at survivors in general, it's only 36%. So there is a drop in the rate when we switch from first class to just everybody, okay? Or in other words, there's an increase in the rate, survival rate, if we just look at first class. All right, guys, that's going to do it for the video. I hope you found this useful and informative, and I'll see you in the next one.